Okay, so this video is going to discuss the properties of electromagnetic radiation. At this point, hopefully you've seen the video about the double slit experiment, and the double slit experiment is a classic physics experiment. It provides evidence that light travels as a wave, and the idea being that when you have other waves, such as water waves, which are really easy to physically see in our world, and you have two waves, the two waves will interact with each other, and they will cause what's called an interference pattern, where sometimes they constructively interfere and create larger waves, and in some places they destructively interfere and cancel one another out, like these spots where the water looks basically entirely flat, because in those places the two waves have canceled each other out. And the point is that if you shine a light source onto a double slit, it actually creates the same pattern. So the light is traveling through these two slits, but it's traveling through as waves. So on the other side, it creates two distinct wave fronts that travel through. And as they travel out, they begin to cancel each other out in places, such as these dark spots. That's where they're canceling. And they add up and constructively interfere in other spots, such as in the middle is the strongest constructive interference, and then less so moving out. This is nothing that you'll be asked about on the IB exam, but I think it's just nice to have a little evidence for why we talk about light as a wave. This is one of the famous experiments that help prove that or support that. The properties of waves that we really need to know about are their wavelength. Okay, so a wavelength is the length, so it's a unit of length. It could be expressed in meters or nanometers between two crests or between two troughs of a particular wave. The other value we need to know about is frequency. Frequency is, well, how frequent the waves are happening. And really you can think of it as how many peaks are going to pass a given point in a second. So the wavelength is about how long the waves are, how big they are between the crest, and the wavelength. The frequency is how often they are. And you can sort of see from this picture that if waves are longer, then they will be less frequent. And that's assuming that they have the same speed. And that's what we're going to be talking about with light. So shorter wavelengths have higher frequencies and longer wavelengths have lower frequencies. And so that's going to be our relationship. Electromagnetic radiation is a giant spectrum of different types of energy that travels as waves. Our eyes are only tuned to pick up a very tiny fraction of this whole spectrum, and so therefore we call that part of the spectrum the visible portion of the spectrum. But there's lots of other sort of regions of the spectrum that fade into each other. So on one hand side, longer waves are this way, and so longer waves, you can see in the picture they're trying to express longer waves here. Longer wavelengths, which are less frequent and also less energetic, are things like infrared, microwaves, and radio waves. On the right-hand side of this chart, we have things that have smaller wavelengths, getting smaller and smaller as we go to the right, more and more frequent and more energy in those waves. So after visible light, there is ultraviolet light, X-rays, and gamma rays. All of these things are, you could think of them as light, but we really only talk about light is the visible kind that we can see. But all of them are really sort of one and the same. They all travel at the speed of light. So they would all get from point A to point B in the same amount of time. But some of them do so with bigger waves that happen less frequently and with less energy. And some of them are smaller waves that happen more frequently with more energy. This is how it gets represented in the data booklet, section 3 of the data booklet. And so you can see this is the gamma rays, X-rays, UV. They expand out the visible part of the spectrum. Infrared is IR, microwaves, and radio waves, and they give you wavelength values. We already mentioned this, so what is the relationship between frequency, wavelength, and energy? Well, as wavelength goes up, and wavelength is going to get the symbol lambda, lowercase lambda, as waves get longer and longer, their frequency goes down, and frequency is going to be this little V symbol. That stands for frequency in the equations. And as frequency goes down, so does the energy of that wave. Okay? So you can see that energy and frequency are directly proportional with one another, and they're both inversely proportional with wavelength. So as wavelength goes up, frequency goes down, and vice versa. Okay? Now, what do you really need to know for the IB exam? Now, obviously, this is you'll get to use this table on paper 2, And I'm going to show you the equation that's also in the data booklet that you might be asked to use on paper 2. But on paper 1, really what you need to be aware of is this portion of the spectrum. Everything between UV and infrared. So there is a simple way, a simple mnemonic that you've probably heard of before to remember the colors of the rainbow. That's Roy G. Biv. Here it's been written backwards just because of how they've decided to order the spectrum. But usually we represent it as Roy G. Biv. So red, orange, yellow, green, blue, indigo, and violet. So that's the order of the electromagnetic spectrum, the visible part of it. And then it should be pretty easy to remember that on the other side of red is the infrared, and on the other side of violet is the ultraviolet, right? And then so basically what I'm pointing out is that these parts of the spectrum should be fairly easy to remember their order, red and violet, so it's not too hard to come up with infrared and ultraviolet. If you're trying to remember, where's higher energy, where's higher frequency, I remember that ultraviolet is dangerous. I think we probably all have just a gut feeling. It's been pounded into us that UV rays are going to be bad for us. They can cause skin cancer. That's why we put on sunblock when we go out in the sun. So UV light, I know, is dangerous for me because it has high energy, and if I'm exposed to a lot of it, it can cause damage to my cells and so on. So high energy, and this side is low energy, and then from there, you can hopefully remember the other relationships. Like low energy means low frequency, and it means high wavelength. And so it means the opposite for the other end of the spectrum. There's going to be high frequency, and it's going to be small wavelength. Okay. These are the types of questions that you could get on paper 1. They could say, okay, here's infrared light, here's yellow light, and here's blue light. Put them in order for energy or for wavelength or for frequency. And if you can come up with this, what I've written in this box very quickly, then that question is going to be really easy. It shouldn't be difficult to answer. So remember your Roy G. Biv, remember how infrared and ultraviolet radiation fit on either side of that, and remember how they work for energy, frequency, and wavelength. That you should be able to explain from memory without the help of the data booklet. Now, with the data booklet, you get this equation. C equals V times lambda. So this equation is telling you that the speed of light, let me shrink this down. So the speed of light, which is a constant in a vacuum, so the speed of light, which is 3.0 times 10 to the 8th meters per second, 300 million meters in a second, pretty darn fast. Since that's a constant, for all different types of light, then we have their frequency times their wavelength. And hopefully you can recognize that if speed of light is a constant, then if I have a constant equal to 2 values being multiplied, that looks an awful lot like the P1V1 equals P2V2 equation. So this is an inverse relationship. If they're always going to equal the same constant speed of light, then as frequency goes up, wavelength will have to go down by the same factor so that they still equal the same speed of light. In terms of units, you've got meters per second is speed. Frequency is the number of peaks per second. So really the unit just ends up being a per second, since a peak isn't really something we can express as a unit. So frequency is always expressed as per seconds, and wavelength is a length, so it's best to express it as a meter, a unit of length. Now you may see it given to you in terms of a nanometer, so you're going to have to be able to do that conversion, and we'll talk about that in a second. So that's how the units work out. In the HL class, there's another equation down here, topic 12, so this is the HL portion of atomic structure. There is an equation that allows you to calculate the energy of a photon of light, a particle of light, based on its frequency. So the frequency is V, H is called Planck's constant, and then E is the energy of that light. So if you look down at the bottom here, here's the table of constants. So what are we going to use? The ones that are going to be helpful to us now, here is the speed of light. Notice they didn't tell you that its symbol is C. It's also kind of confusing because the specific heat capacity, which we've already covered, also gets the symbol C. So you really have to know what this equation is talking about. So this symbol C in this equation means the speed of light. And the speed of light is given to you here, 3.00 times 10 to the 8th meters per second. If you're an HL, Planck's constant, they give you the symbol for that is H, 6.63 times 10 to the negative 34th joule seconds. So the units are joules times seconds, which will make times frequency, which is a per second, cancel out and give you joules for energy. Okay. Again, units that we're going to use, I've already kind of highlighted them. The main thing is that watch out with wavelength. If you're given nanometers, like let's say they tell you that the light is 450 nanometers. Yeah, I can write a 0. There we go. Sorry, marker. Okay, if you want to write it as meters, just tack a 10 to the minus 9 on it. Nano represents billionth. So if you're going to write it in meters without thinking too hard about the conversion, you can just write 450 times 10 to the minus 9, and now you've written it the same length in meters. So 450 nanometers is 450 times 10 to the minus 9 meters. The nano, the little n, basically means times 10 to the minus 9. So a quick conversion. You should know how to go between joules and kilojoules, dividing by 1,000. And if you can do this simple stuff, then you can use the equations. There are a couple practice questions here that we can try in class, including ones like paper 1 style questions where you need to rank things. But yeah, that is the extent of what you need to know for electromagnetic radiation. Understanding the relationships between wavelength, frequency, and energy for light, being able to recreate those relationships for this part of the electromagnetic spectrum. And then on paper 2, using this equation, C equals lambda V, and this constant, 3 times 10 to the 8th, to perhaps calculate a frequency or a wavelength. And in the HL class, using this equation to calculate energy based on frequency or wavelength based on energy. So that would be, the trickiest thing would be to give you an energy. You would then have to work backwards to calculate frequency. You could then plug the frequency into this equation to solve for a wavelength. But again, that's only an HL topic. So yeah, those are the properties of electromagnetic radiation you need to know for the IB exam.